to welcome Daniel Peralta-Salas, who will give his talk on knotted vortex tubes in the Euler equation. Daniel, 40 minutes.
Thank you. So first of all, I'd like to thank the organizers for the kind invitation to give a talk here. Can you hear me? Is it working well? Yeah. Okay. So as I said, I'm going to talk about knotted and also linked vortex tubes in the Euler equation. So these are the equations. I will consider in the talk that the fluid has constant density. So here the U is, as usual, the velocity field and a non-autonomous vector field. And P is the pressure function. The domain here in this talk will be always R3, the whole R3. And later I'll say something about, say, boundary condition at infinity or behavior at infinity. So this is an equivalent way of writing the Euler equation, which is convenient for our purposes in terms of the Bernoulli function B. And some notation which is important for the rest of the talk is the concept of streamlines. These are just the integral curves of the velocity field as a non-autonomous vector field in R3. The interpretation is just the fluid particle trajectories. And also the vortex lines, which are the integral curves of the vortex of the vorticity, which is just the curl of U. And these integral curves are considered for fixed time. So now I'm going to introduce the main star of this talk, which is the concept of vortex tube, which is the following. So we say that a domain in R3, whose boundary is a smoothly embedded torus, this is a tube in R3. So we say that it's a vortex if it's invariant under the vorticity flow, under the vorticity vector field. So this is equivalent to saying that it's the union of vortex lines. So in this talk, I will always consider this kind of closed vortex tubes. Sometimes in the literature you can find open vortex tubes, which are diffeomorphic to cylinders. But in this talk, vortex tube will mean this object, which is a manifold whose boundary is a smoothly embedded torus, right? So this is the most important object in this talk. We are going to study these objects. And the main problem, the question that we will consider here is the existence of these objects. Do there exist knotted and linked vortex tubes in steady solutions of the Euler equation? So by steady, I mean that the velocity field doesn't depend on time. So the Euler equation just reduces to this couple of equations, V being the Bernoulli function. And here the concept of knot and link, this refers to the embedding of this boundary of this torus, which does not need to be trivial in general. So by knotted tube we mean a smoothly embedded solid torus in R3. And if we have a disjoint union, pairwise disjoint union of knotted tubes, we have a link set of vortex tubes. So for example, non-trivial knotted and linked tubes are this one here in the shape of a trefoil knot, and on the right you have three vortex tubes. Individually they are trivial, but the union is not isotopic to say to three vortex tubes which are separated by a plane. So this is in the shape of the Borromean rings. So this just illustrates that the way of embedding these tubes does not need to be the trivial one, the revolution torus or a union of revolution tori. So what's the motivation to consider this problem on the existence of knotted and linked vortex tubes? First, in the non-steady situation, I will always consider steady situation, but there is a first motivation, which is the non-stationary case, and which is just the well-known phenomenon of vorticity transport. It's the equation, the Euler equation for the vorticity is just this transport equation, which can be formally integrated, say, in terms of the flow of the non-autonomous flow of this velocity field U. And this says that the vorticity of time t evolves with a diffeomorphism from the vorticity of time t0, always assuming, of course, that you have a solution for the Euler equation, that it evolves well and it doesn't develop any kind of blow up or singularities. So the topology prescribed at the initial time will be conserved with time up to blow up. So, but this is the non-steady case, the time dependent. So in the steady situation, a motivation is this conjecture by Lord Kelvin, which says that knotted and linked vortex tubes should arise or can arise in steady solutions to the Euler equation. And in fact, he added the word thin here, which means that the width of the vortex tube should be small in some sense. That will be made precise later. Will be small compared with the length of the tube, and this is this is in all the considerations by Lord Kelvin. These thin vortex tubes, in some sense, that will be made precise later. Sorry. So another motivation is a heuristic, very nice argument due to Moffat, which is based on the magnetic relaxation phenomenon, and this proves this argument proves the existence of a stream of knotted and linked of any topology string tubes. By string tube, I mean exactly the same definition of a vortex tube, but the invariance is not under the vorticity flow, but under the flow of the velocity field. So, and this argument doesn't work for the vortex tubes. It can prescribe only this kind of string tubes. Tubes invariant tori which are invariant under the velocity field. And more motivation is a lot of work by Rika and collaborators using the approximation of the LIA equation, also Biot-Savart law, and also there is much numerics about these kind of things, and also there are exact solutions with axis symmetry. You have revolution tori, etc. So all these things motivates to study the general case of considering the existence of vortex tubes in the shape of any knot and link that one can imagine. So in our approach to this problem, we will consider Beltrami vector fields, which are vector fields which satisfy this PDE in R3. We are always working in R3. Curl of U equal lambda U. Here lambda is a constant, different from 0 in this talk. And it's easy to see, well known, that these Beltrami fields are steady solutions, provide steady solutions to the Euler equation with this pressure function. So the motivation to consider this class of steady solutions to the Euler equation comes from a well-known important theorem due to Arnold, which says that in the non-collinear case, in this case, the vorticity, which is curl of U and U, are collinear, of course. So this says that in the non-collinear case, the structure of the vortex lines and streamlines is quite rigid and is ordered in some in a way which is similar, quite similar to the Hamiltonian integrable systems. So and the idea for the proof of this theorem, one of the main points is that in the non-collinear case, this Bernoulli function that was introduced before is not a constant. So this function not being a constant, it provides a non-trivial first integral for the velocity field and also for the vorticity field. And then the level sets of this first integral of this function provide or give rise to this partition or kind of foliation of the space or of your domain. And the lines of the vortex, the vorticity lines and the stream lines lie on this foliation, and then that's why it's ordered this behavior, the behavior of the velocity field and the Beltrami field. So, but this you can't have this kind of a structure in general for a field of this type, because in this case we have that this is collinear, the curl of U and U, and therefore the Bernoulli function is trivial, is a constant. So in fact, Arnold in his 1965 paper, he conjectured a quite general conjecture, which is wide open today, that that in the collinear case, specifically for Beltrami fields, they could present vortex lines, also stream lines of for Beltrami fields. Of course, vortex lines and stream lines are the same because they are collinear. So they should present the same topological complexity as trajectories in celestial mechanics. This meaning in a bit more precise sense that one can have a portrait for your field of the same complexity as a divergence-free vector field in a free manifold. So essentially, you should have chaos, you have many invariant tori, etc., etc. And at that time, also in a paper in 1965, I think, there was some numerical evidence of this kind of things, studying a particular family of solutions for the Beltrami field, which is the ABC family, ABC solutions, which are explicit, very simple way of writing them, but very complicated way of studying the qualitative properties of these solutions. And this Enon numerically saw that there are these kind of complicated structures for some parameters of the ABC family. Okay. So, and another motivation to consider Beltrami fields is that recently we have proved with my colleague Alberto Enciso, he's also in this room, he will give a talk after me. And in this paper we prove that a kind of realization theorem, not for vortex tubes, but for vortex lines or stream lines, they are the same as I said for the Beltrami fields, proving or saying that any link type that you can imagine in R3, if the link consists of finitely many components, or maybe infinitely many but locally finite, then that this can be realized by up to say a small diffeomorphism of R3 by a Beltrami vector field. Okay, so it's natural to consider a more difficult case, which is not the case of the lines, but the case of the tubes. So the question, the initial question that we pose concerning the state solutions of the Euler equation, we can fix a particular family of state solutions to the Euler equation, and instead of dealing with the general case, we can focus just on Beltrami vector fields. So, do there exist noted and linked vortex tubes for Beltrami vector fields? That's the question that I'll consider for the rest of the talk. And just a remark is that if one cares about finite energy, this is bad news, because any Beltrami vector field has infinite energy, because in particular it satisfies this equation here, Laplacian plus lambda square u equals 0. So it cannot be in L2. Okay, so any approach to this kind of realization problem will provide solutions with infinite energy, but we will be able to control the behavior at infinity to get some decay, etc. You will see what kind of behavior at infinity will have, but the solutions will not be in L2. Okay? They cannot be in L2. So now I'm going to state the theorem that we have proved in this context. So for this, we'll consider thin tubes, which is in fact it's something essential for our approach. You will see later when I sketch, say, the proof of the theorem, that we need thin tube in the following sense. So so we define the concept of thin tube, and it's quite convenient to define this concept, the concept of metric neighborhood of a curve. So we have gamma, which is a smooth closed curve in R3. We define this set T epsilon of gamma, which is say a tube of core gamma, thin tube of core gamma and thickness epsilon, and it's just given by the set of points which are to distance smaller than epsilon to the curve gamma. It's just a tubular neighborhood of the curve gamma, but of constant or of distance smaller than epsilon. So this is a tube. This has the topology of a solid torus embedded in R3, which can be, of course, noted if the core curve gamma is noted itself. And of course, it's very easy to check that any finite collection of tubes in R3 can be isotope to a collection of thin tubes in this sense. Okay, that's just compressing each of the tubes. You can deform retract over some core curve that you can define inside, and this is very easy to check. So this is the theorem that we have proved with Alberto Enciso, and the statement is the following. So we have in R3 we have a set of n pairwise disjoint closed curves, always smooth curves, gamma 1, gamma n, possibly of course noted and linked, and we consider for some small enough epsilon, this small enough will be quite precise, or it's quite precise in the computations, but okay, for the moment, let's say small enough epsilon, we can define the set of thin tubes associated to this configuration of curves. This way, you have just the tubular neighborhoods, the metric tubular neighborhoods of this set of curves. This define this object for each one of the curves, and you consider epsilon small enough. Then for this set of tubes in R3, finite set of tubes, then the theorem is that we can transform, we can deform this set of tubes by a diffeomorphism phi of R3, which is arbitrarily close to the identity in any CK norm that you want, so that the transformed set of tubes, this phi t epsilon gamma 1, phi t epsilon gamma n, is still thin tubes because this phi is as small as you want. Then these are thin vortex tubes of a Beltrami vector field. This means that this transformed collection of tubes now will be invariant under the vorticity vector field of a vector field u, which satisfies this equation, curl of u equal lambda u in R3 for some constant lambda which is not 0. So being a Beltrami vector field, this is of course an analytic vector field, analytic solution. And here this epsilon, this parameter epsilon will be any epsilon smaller than some constant, say epsilon 0, and this thickness just depends on it's a universal constant which depends on the geometry of the curves that you have prescribed at the beginning, and of course on the smallness of the diffeo that you want to get.
Transform tubes at varying widths are constant.
The transform, yeah, no, they don't need to be metric neighborhoods. Yeah, they don't need to be. They are very close to be metric neighborhoods, but not necessarily. Yeah, of course.
Epsilon is a constant in evolution.
This is a steady solutions of the Euler equation. So it remains always fixed. So, but moreover, so we have this is the realization theorem. We have this set of tubes in R3, and we can deform this set of tubes in vortex tubes of a Beltrami vector field. Okay. So, but we have more in the theorem. We have that there is very rich, say, dynamical structure inside of each tube. Okay. These tubes are thin, but they are not infinitesimal. So, so they have some thickness, although small in some sense, in the sense that the thickness has to be smaller than certain constant, which depends on the geometry, essentially. And so, therefore, you can have very, very rich structure for the dynamical system that is defined inside the tube. And indeed, we have this structure. So we prove also in the theorem the following things. The first one is the behavior at infinity. Does it decay? How does it behave? Is it in L infinity, etc.? So what we prove is that we can take these solutions, these Beltrami fields, so that they decay at infinity, not only the vector field, but all of its derivatives, as 1 over x. And so therefore, in particular, they are in LP for any p bigger than 3. Okay. So a second condition or second property that you have inside each of the tubes is that there are infinitely many invariant tori which are nested invariant tori inside of these tubes, and on each of these invariant tori the flow is ergodic, meaning that the vector field, the velocity field or the vorticity field is conjugated to a linear vector field with irrational rotation number, not only irrational but Diophantine. So you don't only have a tube, say, but you have infinitely many tubes, one inside of the other. Just say in a KAM scenario. But this is not integrable possibly. But I'll say something about integrability later. Moreover, you have also we started with these thin tubes. We started with these thin tubes and we constructed then with a core curve. Okay. Now with the deformation, this new tube is not a metric neighborhood of your core curve. But what we have is that there is a closed vortex line which is very near to the initial core curve that we prescribe. And in fact, this closed vortex line is stable in the following sense. It is linearly stable. It is elliptic. Linearly stable, I mean ellipticity doesn't mean stability. But in this case, you can prove that it is indeed also Lyapunov stable. Okay. And moreover, this infinite set of invariant tori that you have inside each one of the tubes, we can see that it has positive measure. It's not small, this set of tori. Okay, and you have positive measure both in a small neighborhood of the boundary of the vortex tube and also in a small neighborhood of this core vortex line that you have inside, say, at the center of the vortex tube. And moreover, finally, you have also infinitely many closed vortex lines inside the vortex tube. And in general, none of them have the same knot type as the core vortex line. The core vortex line have the same knot type as the initial curve that you prescribe. But these closed vortex lines that you have, many more than just the core vortex line, these are usually cables of the core vortex line, or maybe more complicated structure. Okay, so this is the theorem that we have proved. And some remarks here is that, well, first, now when I sketch the proof, we'll see that the thinness of the tube is a crucial assumption. This is very necessary. We cannot prove the result with this kind of thinness hypothesis. Second one is this decay. We prove this decay of 1 over r at infinity. This is optimal. You cannot get anything better for a Beltrami vector field. This is the best thing that you can get. Okay. And a third remark is that these tubes, this structure of tubes, is stable in a twofold sense. First, you have, say, stability in the sense of structural stability. So this meaning that they are robust under small perturbations of the vector field in some CP norm, say. Then if you perturb your vector field, a vector field which is nearby your Beltrami vector field, not necessarily another Beltrami vector field, then you will have the same structure of vortex tubes. Okay, they are structurally stable, and this come again from KM theory and the kind of prescription or the kind of structure which comes from the PDE. You will see this later more clearly. And a second kind of stability that we have is that both the boundary of the tube and the core vortex line, they are Lyapunov stable. This meaning that if you have a vortex line which intersects a neighborhood of your core vortex line of your tube, then it will remain in a neighborhood, essentially. Okay, there is a precise definition of Lyapunov stability, but this essentially means this thing. Yeah.
Do you mean you don't mean intersection, approach itself?
Well, here meaning that the vortex line intersects the neighborhood. No, the vortex lines don't intersect. So it's just if you have a vortex line which is, say, at some moment it's near the tube, it will remain near the tube for forward and backward in time. Okay. So, a corollary of this result, since we have these tubes, and inside each one of these tubes we have this core vortex line, we have as a corollary as our previous theorem on the fact that any link can be realized up to small diffeomorphism by vortex lines of a Beltrami field. This is indeed a corollary of our new theorem, but we have more than before, because before we didn't control the behavior at infinity. Now we can. We know that you have decay at infinity, not in L2 but in L4, say. But and also we have stability of our core vortex line. In our previous paper, Alberto will talk about this. The vortex line is hyperbolic in the exact meaning of hyperbolic definition, which meaning that, say, the Lyapunov exponents have non-zero real part. And in this case, you have that the multipliers have modulus equal to 1. So they are stable, they are linearly stable, but moreover they are Lyapunov stable. So, and okay, I'll skip this and I go directly to give some ideas of the proof of this theorem. So the problem with this kind of results is that you have to extract this kind of topological information or geometric information from the PDE, and that's usually complicated. If one tries a purely topological approach using purely topological technique, this is too soft to capture the PDE, and usually you lose the PDE. For example, this can be seen very clearly in the Naden-Grice approach using contact geometry or contact topology, where you can prove this you can realize this kind of complicated structures, not only lines but tubes and also chaos, etc. But you lose the PDE. You have to change the metric. So you cannot have results for, say, the canonical round metric in S3 or for the Euclidean metric in R3, etc. So you have to change the equation to be able to use this kind of topological tricks. And on the other hand, using just purely analytical techniques without taking into account, say, the topology or of the phenomena or of the structures that you want to prescribe, this has been quite successful, for example, for the 2D case, using variational techniques, as for example in this approach, Lawrence and Stredolinski. But for the higher dimension, the 3D case, this has not been, at least for the moment, quite successful using just purely analytical techniques. So in the approach that we follow, it's a kind of mixing. We use arguments both from the topological or dynamical system side and also from more analytical or PDE side. And say that the strategy of the approach is quite simple. It's first we want to realize some structure. So what we do is to construct or to prove the existence of some local solution of some local Beltrami vector field, which realizes this topological structure. For the moment, local vector field, and moreover, we do the construction or we get a construction for which this structure is robust in some sense. And then after this, say, local construction, we approximate the local solution by a global solution. You cannot extend a local solution by a global solution. This is not possible in general. But what we would like to do is to approximate our local solution by a global solution in a good uniform sense, so that the robustness that you have for the local solution preserves the topological structure that you have at the beginning. So your global solution will still have the same structure. So this is the strategy, say, that we try to apply to this problem. Exactly the same strategy which was done in our previous work with Alberto, but in this case it's much more complicated. Both the local solution, the robustness properties, etc., are much more complicated. So let me comment now something about this. So first, the construction of the local solution. In this case, is the problem with this is that we need to control the local solution in some sense, and controllability here means that we have to check some robustness properties. And this is, of course, here our local solutions are not explicit, so it's complicated usually to check the kind of properties that we will have to check. So for this, well, we use a kind of indirect argument. So first we endow a metric tubular neighborhood of the tube, of each one of the tubes with a natural coordinate system. So for if the core line is smooth and it's generic, then you can endow the tubular neighborhood with a very natural coordinate system, which is using this E1 vector field and E2 vector field, which are the normal and the binormal vector fields. This is well defined for a curve without inflection points, and the fact that a curve doesn't have inflection points is generic for smooth curves. So you have a kind of natural coordinate systems, and then what we do is not working directly with Beltrami fields, because this is complicated. I'll say something later why it's complicated doing directly the things with the Beltrami fields. But first you work with harmonic vector fields inside each one of the tubes. So harmonic vector field means just a vector field H, which is unique up to a constant because of the topology of the tube. And it's a vector field whose divergence is 0, curl of H is 0, and is tangent to the boundary of the tube. So this has the following expression. You have a first term which is explicit in terms of this coordinate. This tau here is the torsion of the curve. Here this is an explicit function which depends on k, which is the curvature of the curve. But here you have the gradient of some function psi, and this function psi is not explicit, but you know that it satisfies an elliptic Neumann boundary problem in each one of the tubes, which is the Laplacian of psi is equal to some function, which in these coordinates that we introduced before. Here we have already introduced the parameter epsilon. just by rescaling your coordinate system. So in these coordinates, this is of order epsilon. Okay, and this Laplacian in coordinates alpha and y. This Laplacian also depends on epsilon in a singular way, in fact. So you have this problem, and which is of Neumann type. So the normal derivative at the boundary of the function psi is 0. So the point with the harmonic vector field is that it is not easy. So the harmonic vector field doesn't have an explicit structure. If you want to control the geometric side, if you want to understand the orbits of the harmonic vector field as a dynamical system in the tube, this is not easy. And to do it, what we have done is, okay, we can control something, not everything, but something, if we assume that the tube is small, that this epsilon, this is a parameter epsilon which is in the equation. So say epsilon being small enough in some sense, then we can use a kind of perturbative argument to understand the structure, some of the structure or enough structure of our harmonic vector field inside of the tubes. So for this, we need a kind of pointwise estimate which is uniform, well, not only uniform but optimal, which has optimal behavior with respect to this parameter epsilon. And then we have proved a first intermediate result, which are just some CK estimates for this function psi inside of the tubes, and these estimates have to be optimal in the sense of having, for example, here for the y derivative, we need this cube power here for the epsilon, because we need at least this control here to control the gradient of the function psi. Okay, so now with this and with the idea of taking this epsilon small enough, we have, say, the harmonic vector field. And now we want to pass from the harmonic vector field to the Beltrami field. So the next idea is, okay, just the rough idea is, let's try to approximate your harmonic vector field by a Beltrami vector field in such a way that if your parameter lambda of your Beltrami vector field is small, then this should be something like v equals h plus O of lambda. Okay, this is not possible for a closed manifold without boundary. Harmonic vector fields or harmonic forms and Beltrami are orthogonal, L2 orthogonal, but this is possible for manifolds with boundary, because it's the Beltrami fields in a manifold without a boundary of this type, say of a torus, of a solid torus, are very, very complicated. They are not as much as in R3, but they are more than, say, the Beltrami vector fields associated to a self-adjoint problem to the, say, Higa-Yoshida spectrum. You can define a spectrum for the Kell operator, and this gives a discrete spectrum, but outside the points of this spectrum, you have more Beltrami fields also. And that's why you can prescribe the harmonic part of a Beltrami field inside a tube. So you have to prove this theorem, that for some values of lambda, say capital lambda, fixing some capital lambda, that you want, and then for small enough epsilon, you have Beltrami fields inside the tube, tangent to the tube, to the boundary of the tube, such that the harmonic part of your Beltrami field is prescribed. It's exactly given by the vector field H that we constructed, say, before. And you have a very good uniform estimate or difference between your Beltrami field and your harmonic vector field. And this constant here, this is indeed what we wanted, something which is small if lambda is small, and this C, in fact, you have to prove that it's uniform, doesn't depend both on lambda and on epsilon. Okay. So the conclusion is that taking, say, epsilon and lambda small enough, you can do quantitatively all these small enough things, but this requires more machinery. So here, just I'm saying this say qualitative statement of small enough. Then you have your local Beltrami solution, and you can, say, control it more or less. So, and just a comment on just prescribing directly, because one can work with Beltrami vector field on the tube, tangent to the tube, and then one can try to prescribe a boundary value problem for the Beltrami field, but this is not possible. In general, you cannot prescribe. This is not like an elliptic problem where you can prescribe the value of your function at the boundary, etc. Here, in general, there does not exist a solution to the boundary problem for the Beltrami field with a prescribed value at the boundary, okay, tangent value of the boundary. So that's why we use this trick of first working with the harmonic fields and then trying to approximate them. So now, yes, we have this local solution. We have we need this control, this robustness. The natural tool is K-and theory. So for this, we have to compute some quantities associated to K-and theory, the frequency or the rotation number of your Poincare map on the boundary of the disk, and also the normal torsion, which is this doesn't have anything to do with the torsion of the curve. That's a kind of non-degeneracy condition for K-and theory. And then for generic curves, you can prove that this omega is the phantom, which is necessary to apply K-and theory, and moreover that this twist condition is verified. This is different from zero. Okay, so you can prove at the end of the day for Beltrami vector fields a kind of K-and theorem, which says that if you approximate your local solution by a global solution, then you have the preservation of the invariant of these invariant tubes that you have for the local solution. Okay, but here this is delicate, the application of K-and theory here, because first you have the perturbation of a vector field or of a map of constant frequency, and second, this is not the usual setting for K-and theory. This is not Hamiltonian context. It's divergence free, but not Hamiltonian. There are no action angle variables. There is no usual twist Moser Moser twist condition, etc. So you have to do things very carefully. And for example, here is very useful the application and the adaptation of a theorem by De La Llave. So and finally, it can be proved a theorem, which is an approximation theorem. If you have your local solution, you can prove using a kind of variation of a Runge type argument or technique, and controlling also the behavior of the field at infinity, that you can approximate your local solution by a global solution with this decay. Okay, and and finally, if you put this everything together and this estimate, etc., 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 then you can prove that then you can apply this to each one of the tubes, and then you can prove the realization theorem. And to prove the richness of this geometric structure of the lines inside the tube, you have to do a bit more. But now with all these previous results, it is not so difficult. You just have to compute the monodromy of the vortex line, of the core vortex line. This is not difficult. And now you have just to apply some well-known theorems in dynamical systems adapted to this constant, to this context. But this is not difficult. You just have to apply Hermann's last geometric theorem, which is not due to Hermann, in fact, but or the proof is not due to Hermann, but it's called Hermann's last geometric theorem, and also Birchhoff's and Smel's theorems. Okay, and okay, just as a final remark, and I'm finishing just right now, it's that we believe, we feel, we think, we guess that there is chaos inside each one of these tubes. And I bet my hand, left hand, that there is chaos inside here. But chaos in the sense, for example, of positive topological entropy. But okay, this is work in progress. For the moment, we have not been able to prove it because because it's the topological entropy. It's very possibly is exponentially small with the parameter epsilon, so that's not so easy to detect. But okay, that's I guess. So thank you very much.
Very good, Daniel. Questions, please. Yes, Steve.
In the global solution, the tubes have to stay pretty far apart, in some sense.
No,
How close? How close?
Can they get close together? Is what I mean.
they can be close together, more or
Okay.
less. I mean, they don't touch. But in fact, you can have the same kind of global solution if you have infinitely many tubes, but locally finite, and they approach more and more as you go to infinity. You can get a kind of better than uniform approximation for this.
Can they get within epsilon?
And the epsilon will have to go smaller and smaller as you go to infinity. Yeah.
Carlo.
We found numerically Gross-Pichayevsky and Biot-Savart knots, which were relatively stable up to a certain time, but they were all time dependent. So what keeps your knot structures steady? I fail to see it. You got vortex lines close to each other.
Well,
Why
they
do
are
move?
steady solutions. So
What
they
prevents the rotation in any direction? Is that the Beltrami condition?
Yeah, well, they are Beltrami vector fields, so that's why they are steady solutions. They don't develop with time.
When you look at the stability, do you look at the stability with respect to any perturbation in three-dimensional
So
space?
you mean, for example, if you have your Beltrami field and you see what happens for a vector field nearby, for example, this? You mean this? Or?
The nearby vector field is autonomous, not.
It's sorry?
The nearby vector field is steady.
This is partly what it's asking. When you
No,
perturb,
the general vector field is not steady. I mean,
no, when you do your perturbation theorem is for nearby steady.
this, yeah, here everything is steady. All the vector fields are Beltrami. Exactly.
Right, and
So
the near-
steady.
Yeah, so the
Everything
near-
is steady
right,
here.
So it's the Apanov stable with respect to steady perturbation.
Everything is steady. With respect to Beltrami fields. Yes, exactly.
But you don't talk about the dynamical stability of these in the context of the Euler equation.
No, this we don't know. Yeah.
They're very likely unstable.
Possibly. For example, there is this result by Friedlander and Bischik, which relates the stability with the Lyapunov exponent. Here, this kind of structures, this elliptic orbit, etc., they don't have this positivity of Lyapunov exponent, but possibly if there is chaos, there will be some kind of hyperbolicity inside of the tube. So possibly they are unstable in this sense, but we don't know.
Could you just draw such a structure just to build our intuition how it may look?
Can
The
you
structure of the
Yeah.
inside of the tube, yeah.
No, not inside. I mean of
outside.
two interlinked tubes. Can you just draw it?
Yeah. For example, you have the boundary of your tube, and typically what you have is here inside. This is a section, say, of the tube. Okay. So here you have the intersection with a vortex line, which is this point, and it's elliptic in the sense that there are elliptic and also Lyapunov stable. So this means that there are infinitely many invariant tori also nearby this point. And also you have also infinitely many invariant tori nearby this boundary. In between, we don't know, possibly chaos. It's a typical situation, but modes, and possibly you have this kind of homoclinic tangles, which is here you have a periodic point, you have a stable and unstable manifold, and you have again intersection, and then reproduces again and again, and you have this kind of chaotic structure. But this we don't know. We only know the existence of this invariant tori. This is not a continuous. This is not a continuous. We have a positive measure set of invariant tori, but this invariant tori don't fill everything here. I mean, this is not a continuous family of invariant tori, possibly, and also the same with this.
So all these tubes are embedded in one invariant tori, right?
They are all nested. Yeah.
Uh-huh.
Yeah. Inside this.
Marie?
Yeah, this reminds me a little bit of some solutions that Robert Krasny was having in a kind of, well, he was studying kind of Kelvin-Helmholtz instability like that. But what you were finding, though, there was a very tiny piece of chaos, which was starting exactly the way you are kind of describing it. Maybe, I mean, of course, there are numerical simulations, just, but this kind of structure, I already have seen it in some solution of this.
Yeah, this is possibly the typical situation for this kind of fields. Yeah.
Yeah, the very beginning of the construction is local, and then you need to worry about extension outside. Do you really need the topology of R3, or can you do it in periodic boundary condition?
You can do it in any open manifold, but you can't do, for example, if you are in a domain with some tangency boundary condition. This you can't prove this kind of approximation here. We don't know how to prove it. Yeah. We need infinity, say, and in R3 or any other open manifold, you can do the approximation just controlling, say, the decay or something like this, but you can't control so much as boundary conditions. So, yeah.
So periodic boundary conditions, you can do it.
No, for example, in the torus, in the three torus or something like this, you can't. Or, well, we can't.
Okay, I understand.
We don't know how to.
We are right on time. Thank you very much, Daniel.